Okay, it's recording.
So everything's good so far? Okay.
Yeah.
Everything is fully comprehensible. Everyone understands everything we've talked about.
No.
Great. 100% hands down. Any circuit that involves a diode I could throw at you, solve it no problem. 5 minutes tops in the crank. As long as there are no capacitors.
It depends on whether we need to show our work or not.
Is there a way of computationally solving circuits
It's
a
kind
little
of the
faster?
context of like if you make your equations,
Mhm.
put them in a calculator and go linear solve, will give you the answer.
Right. Yeah, well, I guess it depends on what I would call showing your work. I feel like the setup, right, writing the equation to begin with, that's the showing your work.
Okay.
The algebra,
Then that's good. Then you have the beginning and the end. That's all that matters. Yeah.
as long as you don't make an algebraic mistake along the way, then that's pretty formulaic. Where you want to show your work is for partial credit and go, yeah, okay, I was solving, and then we could maybe follow along and go, okay, right, flip the minus sign or something, and that's why you got an answer that's backwards from what we were expecting. But I think the algebra is the less vital part. It's knowing how to even write the correct algebraic equations to begin with. That's the hard part of this class. That's the hard part about circuits analysis.
Yes. So showing work is writing the equations in the beginning. That's good to know.
You want to show your work to, I guess, demonstrate that you in fact did solve the problem yourself. That helps. But there isn't like there's some sort of specific detail we're looking for or anything like that.
Right here for the lab?
Lab, homework, and just sort of general
Okay.
life advice, I'd say. So we're at the starting point. Everything is on. I'll hit go. Let this thing actually start recording. All right, welcome to the lecture on January 24th. I'll rocket through a lot of this stuff, and then we'll get back into crystallographic structures and what the silicon lattice looks like. So as a quick state of the course at the moment, we're going to be continuing, hopefully finishing chapter 2 stuff today. Homework 1 is up. It's due on Monday night, I think 11:59 p.m. There are a couple of chapter 3 problems, which are just diode circuits, just solving more of the things that we've solved in class already. The book has many different methods of solving diode circuits and sort of increasing level of detail. Their so-called ideal model is to assume the diode turns into a short when it's on and is an open when it's off. That's even simpler than what we were talking about. Their constant voltage drop model is what we've been doing. Sometimes they call it constant voltage drop. Sometimes some of the problems abbreviated as CVD. That's substituting a voltage source in when the diode is on. And the problems are sometimes 0.7, sometimes 0.6 or something else, just to keep you from getting too comfortable with that magic number and to know that it can change a little bit from situation to situation, mostly depending on how much current you're flowing through. And then they have a slightly more advanced model where you include a resistor, and we might talk a little bit more about that later on, but you basically try to model the slope of the real diode equation and say that's kind of the resistance in this local neighborhood. So we can think of it as even having a resistor and an ideal voltage source. Don't worry about that one on the homework, but just to give you kind of a preview. And then their fourth most extreme method is to use the actual exponential diode equation. That's something you can't really do on paper. You usually have to pull up a computer in order to solve that. We don't want to do that here anyway. So the two chapter 3 problems I've specified problem part B in both cases, and subpart B is to use the constant voltage drop model. They draw all the circuits like I have here with no power supply connected. So if you want to solve it with mesh currents or nodal analysis, then it might help you to redraw the circuit to include the power supply, ground, all that stuff. But the book's illustration of the circuits under analysis are really sparse. They just have stuff like this, where you've got a resistor, a diode, and then it just labels, at this node is this voltage, this other node is this other voltage. To complete the system, complete the picture, you might want to add a couple of sources, and then it should look like what we've been analyzing in class. Maybe that'll be a little more familiar, and then hopefully pattern recognition will take over. And you'll go, oh, okay, I see what pieces I need to solve. I see how to decompose this into some math equations. Lab 1 is continuing. That'll be due next Monday night, just before we start on Lab 2. Sounds like that's been going well for everybody. Sounds like lab yesterday went fine, so I assume that'll be steady she goes. Just make sure you don't underestimate how much time it takes to set up and run all those simulations. There's just a bunch of simulations to get through. It's kind of a speed run of all the lab stuff, so you can see a little bit of examples of all of the devices that we're going to be talking about, but in lab simulation environment instead of in a lecture environment. You probably started to see the rhythm of a kind of quiz style thing after every lecture, and you should be getting notifications about that on Canvas. They're usually going to be due 24 hours later. Sometimes they'll be numerical, like they have been recently, but sometimes, like today's, is just a poll for the class. How are things going? What are the topics that are comprehensible, that are incomprehensible? Where are you at? And we're going to try to ask something like that every week or two to gauge how everybody's doing. On the midterm schedules, so this line at the bottom is what's driving the schedule that I would like to keep. So the course's drop deadline is the 25th of February. I heard some folks talk about other classes they've taken and say, you know, I didn't get enough feedback about how I was doing in the class until after the drop deadline. So my goal is to have most or many of the points figured out, delivered, graded back to you well before that deadline, so that if you feel like you need to drop, you can make that decision earlier. What that means is we probably want to have the second midterm just before that deadline, so that'll be Monday of that week. And that means we want to have the first midterm not like immediately right before, but probably a good number of lectures before that, which means like next Wednesday, which does seem a little sudden maybe, but I wanted to toss that idea out there and kind of get everybody's buy-in. We can adjust the schedule, right? We could have the second midterm after the drop deadline. Also, that's not a crazy thing to do, but if we want to have kind of as many of the major points kind of locked in before that date for everybody's information, this seems like the best schedule to follow. Anybody have any big objections or even small objections to that? We have a midterm. The midterm next week is going to be on whatever we end up being able to get through between now and then. It'll include Monday's lecture. Maybe I'll assign a couple of kind of additional problems, but it'll probably be diode circuits, semiconductor stuff, and maybe some KVL, KCL sorts of stuff. More circuit analysis, and right, no BJTs yet, or very very little BJT material depending on how far we get on Monday. Certainly no MOSFETs or anything like that. It'll just be, we'll just scope it to whatever we've been able to cover up until then. Sound good? All right. So we'll lock this schedule in. I'll create some stuff on Canvas later on. For the folks who are listening to this recording later, drop me a line if you have any feedback on this, but preferably sometime in the next 24 hours so that we can have the schedule really secured. But unless you hear anything otherwise, you can assume that we'll sail forward with this. Great. Yeah, go ahead.
I believe on Canvas it says homework 1 is due Sunday.
Yeah, it is actually. Yeah.
Did I say it's Sunday night?
Yeah.
Okay, that was whatever is on Canvas is. With Lab 1 it should also be due Sunday night then. Yeah.
Lab 1 is Monday.
It's Monday, right? I wanted that to be just before. Well, which one do you want? Sunday night or Monday night?
Monday night.
Monday? Okay, great. We'll call it Monday. Typo on on my side, so yeah, great. So this is correct. Yeah, it's kind of a toss-up. Great, yeah, we'll call it Monday. We'll just have everything kind of stacked up. Good, thanks for pointing that out. All right, any other bits where I've configured the learning management system off that one? All right, great. Let's talk about the periodic table.
Oh boy.
Yeah, hard shift into all of our semiconductor related things. So, where we left off, we were talking about how we start with silicon. We've got this semiconductor that is sort of neither an insulator nor a conductor, but it's kind of in the middle. And if we artisanally infuse a lot of boron or a lot of phosphorus or arsenic into silicon, we change its conductivity, and we change what the crystallographic structure kind of looks like. So we had just started to talk about what that looks like in kind of a 2D illustration way. So if you imagine each of these dots are a silicon atom, each silicon atom has, switch back. Silicon is a group 4 element. It's got 4 valence electrons. So each of these is reaching out with 4 electrons. It sees neighbors, each of which also have 4 electrons, and they end up forming this grid of double covalent bonds throughout the entire lattice. Now this is what it looks like at 0 Kelvin. Everything is stable, all the electrons are where they should be, they're not randomly bouncing around, and we haven't added any impurities. We haven't doped the semiconductor yet. And then what we do is we add some new thing. We fire in, we'll say boron. We'll say this node in the middle, that's now boron. And boron is a group 3. Flip back here. So it's only got 3 electrons in its valence band. So that means we've got one too many lines drawn here. We'll just erase this thing. And what we've got is this gap here that an electron could pretty easily fall into. Looking over the entire web of atoms, an electron could just sort of pop over here. So this electron, the electron designated by this line here, that can move over here, leaving a hole where it used to be, leaving a kind of empty spot. And then this electron could move here, and this electron could move there, and we pretend that that's called a hole, we pretend that that's a real thing, and that instead of electrons sort of cascading towards where the boron has been implanted, we make it look like we think it's a hole that is moving out. And it is able to move about 1/3 as fast as an electron, but it can still move. If we model it, we make it seem like it's a hole kind of traveling in that direction. When that hole takes off, something happens kind of in this area regarding the local charge. So again, we'll flip back to the periodic table. Boron is chemical number 5. So how many protons does it have? Got 5, yeah. That's what we know from the periodic table. And that's how many protons are in its nucleus. How many electrons does it have? It's got 3 in the valence band, but total, it's got 5. That's all well and good, except when an electron shows up and starts hanging around near it. Now there's an extra electron compared to the number of protons that are here. And so this region, when this hole takes off, this region ends up being negatively charged. And it's stuck there. These charges are locked in place. So the hole, when the H plus leaves, the negative charge results. So if you had a much larger tapestry of these, and say every 1,000th node, which is not a bad assumption, say every 1,000th atom is actually boron, and you apply a voltage and you sweep all those holes out, you're going to end up with a big negatively charged chunk of semiconductor, because there's just too many electrons now compared to how many protons are in the lattice. You do the accounting, you add them all up, you add all the protons up, you add all the electrons up, and you've got just too many electrons. There's more electrons there, and so it's the material is negatively charged. This is going to be really important when we start talking about diodes, because we're going to have some materials that have too many electrons and some that don't have enough, and they're going to interfere with each other, and the electrons in the holes are going to flow into each other, and you're going to end up kind of you're sort of washing away these excesses of electrons or holes and exposing fixed in place positive and negative charges that are going to form their own electric fields and then cause other problems with the electron and hole flows that we're starting at the beginning. This is sort of how the diode, the PN junction of the diode ends up appearing, is all of these forces counteract each other. With me so far? It takes a lot of imagination without sort of drawing so many drawings over and over again that you end up with an animation. You kind of have to picture it in your mind's eye. Let's do the same thing, but in the opposite. Let's say we have dropped in arsenic at this spot, and now we've got, just going to draw a line to represent this stray electron that's hanging out there. So it's got 5 electrons in its valence band. The fact that the 5th electron is not part of a covalent bond here means that it takes almost no energy for that valence band electron to pop up to conduction. So it's basically in the conduction band. You basically say this electron is free to conduct around because it's not being held down in any potential well. So this electron, that's probably a lot easier to imagine. You've got a particle-ish, depending on how much you know about the structures of electrons. You've got this thing that just kind of wander around the lattice. So again, we've got an electron that could fly off in this direction. If you apply a voltage, that electron's just going to take off immediately. Now, we'll flip back a couple. We were saying arsenic, right? It's a group 5, so it's got 5 electrons in its shell, 3 electrons in its shell, 4 electrons in its valence band, outermost shell. So 33 is its atomic number. That's 33 protons, 33 electrons. But when one of those electrons takes off, what we're left with is a fixed in place extra proton that can't go anywhere. Meaning that this entire area, if you had this pattern repeating over and over and over again, you have a net positive charge. The electron leaves, but the proton remains, leaving this whole area positively charged. Now at equilibrium, you would expect that maybe an electron would sort of eventually kind of wander back over here. But in electronics, if something's biased, if current is flowing, if a voltage is applied, that's not equilibrium. And lastly, speaking of equilibrium, thermal equilibrium, intrinsic silicon at any temperature that's not 0 Kelvin has some of this stuff happening, just random, just bubbling away. So randomly, a intrinsic silicon will end up with an electron that pops out of its covalent bond and is free to move about the cavity. So this, we end up with an electron hole pair. They get produced that are just sitting locally, and randomly they should recombine, but also randomly they separate, and on average there's a hairy formula that I'll write in a minute that tells you about how many of these per unit density happen randomly at a given temperature. So here we've got the opportunity for an electron to head off in one direction and this hole to head off in the other direction. If you applied a voltage sort of across the diagonal, you would see the hole go in one direction and the electron go in the other direction. And the hole, again, doesn't really exist, but it's just backfilling over and over and over again. So we've got thermal carriers, that's this stuff, and then we've got doped carriers, charge carriers here, that are intentionally added by adding these doping impurities. Boron for so-called p-type, because they're positive, or they end up imparting some positive bias only insofar as you end up with extra holes, and so that's a positive carrier. And arsenic and phosphorus, which are n-type, because they end up imparting more electrons, more freely flowing electrons, and so you end up with a kind of source of negative charges, negative charge carriers. So far, so good? All right, so I promised a big hairy equation. Here it is. The thermal carrier density, the number of intrinsic thermal carriers at 0 Kelvin, 0. Right, there is no thermodynamic activity going on, nothing's happening, so there are none of those random electron hole splits popping out. And at about 300 K, kind of room temperature-ish, we say it's 10 to the 10 per cubic centimeter. We talk a lot in just order of magnitude here because the fine gradations between anything else are just sort of lost in the noise. And even then, off by 1 or 2 orders of magnitude is close enough. There are just so many of these carriers here that the difference between 5 times 10 to the 10 and 1 times 10 to the 10 is a rounding error. We talk about density in all these cases because you can scale all this stuff up to support more current or scale it down to support less. And the actual expression, Ni squared, I always write it in intrinsic number squared, is this material parameter B times the cube of temperature times e to the band gap energy negative over Boltzmann's constant times temperature again. That's equation 2.1 in the book, incidentally. And I squared ends up being units of centimeters to the -6. Doesn't make a whole lot of physical sense, but the math has to work out dimensionally so that you get an answer in centimeters to the -6. So then you take the square root, you get density, you get things per unit volume. B, like I said, is a material dependent parameter that depends on how many vacancy states are available in the material. For silicon, that's 1.08 times 10 to the 31 Kelvin to the -3 centimeter to the -6. For silicon, temperature is in Kelvin. E sub G, that's the band gap energy. that is, we're gonna say 1.12 electron volts. For silicon, that's how much energy it takes to hop layers from valence up to conduction. How much effort does it take? Obviously, with a much larger band gap, the likelihood of there being a thermal carrier that pops up to conduction is going to be a lot lower because it needs to randomly get a larger amount of energy. So wide band gap devices tend to be more valuable for reasons like these, because there are just fewer thermal carriers, which means you have much finer control over doping, and they end up having a much higher temperature ceiling. As you'll see in the first problem of the homework one, is just calculate this twice for a silicon and for a wide band gap material and see what the results are. The results should be shocking. You should see, wow, the number of intrinsic carriers is so much smaller per unit temperature. We must be able to increase the temperature like crazy. And finally, Boltzmann's constant. Oops, what did I just do? Oh, there we go. K. I'm sure everyone has Boltzmann's constant memorized, right? But this is the electron volt version. So before you start pulling out 1.38 times 10 to the minus 23 joules per Kelvin, actually, Boltzmann in EV, it is 8.62 times 10 to the minus 5 electron volts per Kelvin. And since so much of chapter 2 is conceptual rather than mathematical, I'm going to ask everybody to run through this equation once, right now, just to make sure that you've got all the bits and pieces sorted out. So take a couple minutes and calculate what the real density is at 300K. Right? 10 to the 10 is sort of the round number, but what's the actual number if you set T equals 300, right? Again, about room temperature. Punch in all these. If you get that sorted out, you'll have problem 1 in the bag. Turn the crank a couple more times there.
Is that
Yeah.
e to the power of? Or is that
This is, exponential. Yeah, e to the
Okay.
e of, right? Yeah, that's the exponential function. Maybe if I wanted to write it as the exponential function, I would write exp instead. Maybe a little more MATLAB-y. some answers. Hopefully it's something close to 10 to the 10. That's your verification. All right, so it's been 3 minutes. We turned the crank successfully. I see some squinting, you'll have some furrowed brows. Is it just data entry at this point?
I messed up something somewhere, but I don't know where.
Okay. Fair enough. Well, you know what the target is, right? Could be a just a transcription error. You should end up with, I'll write this up here at the top, about 6.7 times 10 to the 9.
Let's go.
All right, so make sure when you run through this expression with 300 Kelvin, you end up with something about that. And then on homework 1, I'll ask you basically increase the temperature until your intrinsic carrier density gets equal to a certain number. That is what sets the maximum operating temperature of a semiconductor-based device. You end up heating up the device so hot that the intrinsic random carriers swamp all the stuff that you've intentionally added. And the concept of a doped semiconductor fails to have any meaning anymore because it doesn't matter. The background noise, essentially, the background noise of randomly produced electrons and holes are dwarfing the amount of electrons or holes you've intentionally tried to add of material. Something with a wider band gap, you have a much higher temperature ceiling. And that's problem 1B in the homework, is just turn the crank again with a different band gap value and see how much hotter you can crank it up. With silicon carbide, which is the material of interest in the homework, that stuff is what you put in turbine engines. You put that inside of nuclear power plants. It can get so fantastically hot and still operate just fine because the number of intrinsic carriers is still so low at really, really high temperatures. Now, the answer you get in problem 1 is going to be probably way higher than it should be because I've given you a new band gap and not a new material parameter here. But it should give you a sense of the trends anyway. All right, good so far? Let's talk about dopant accounting. So let's talk about all those dopants. How do we refer to them? There's going to be maybe a bit of jargon thrown at you. So dopant, start with density. Typical is something like 10 to the 14 to 10 to the 21 atoms per cubic centimeter. 10 to the 21 ends up being about the ceiling because silicon is about 5 times 10 to the 22 atoms per cubic centimeter. So if you go too much past 10 to the 21, you start to end up with a block of boron instead of a block of doped silicon. So 10 to the 21 tends to be about the upper ceiling. If you add boron to some density, we call that density the number of acceptors. N sub A. The number of acceptors, that's the density. So if you add 10 to the 14 per cubic centimeter, that's Na now. So the number of acceptors you've added to a chunk of silicon, that's Na. You add arsenic or phosphorus, that's the number of donors. And you kind of get maybe some intuitive sense behind these names. And donors, they donate electrons. Acceptors, they accept electrons. The dopant density Na or Nd is related to what we generically call P and N, where these are the actual concentrations of holes and electrons that result. Right, so Na is the number of, in this case, boron atoms, and P is the number of holes that you end up with. They're close, they're always really similar, but not always equal. So they don't necessarily equal each other. This is the holes per cubic centimeter and the electrons per cubic centimeter. The new holes introduced and the electrons introduced. You can imagine, for some strange reason, you take a single piece of silicon and you add a bunch of acceptor atoms, and then you add the same number of donor atoms. Well, all right, you're not going to end up with a hole density and electron density that is equal to either of these numbers. They're basically going to annihilate, and you're going to end up with nothing. So you spend a lot of energy to make some weird soup of atoms that isn't necessarily doing anything. But you can imagine, right, there are maybe bleed-through situations where you're doping one area of the semiconductor, you're doping another area, and the regions overlap a little bit, and so there is some hybrid middle ground where they annihilate each other a little bit. Or what happens frequently is you start with a chunk of silicon and you lightly dope it with just a little bit of p-type material. And we tend to annotate that by saying p minus or p plus or p plus plus to say relatively if this is a little bit or a middle amount or a lot or a whole lot. It's common to have a silicon wafer that is uniformly p minus a little bit. And then if you want to turn that into an n-type device, you diffuse some n into that, but it's dealing with having a little bit of p-type material in there already. So that's going to subtract from the efficacy of all the donor material that you're adding in. The book has an exact equation given how many acceptors and how many donors, what sort of hole and electron densities you should expect. That pretty much never happens. It never ends up being relevant. So we're actually just going to say these are approximately equal. As long as that's the majority, right? So you take a semiconductor, you add a whole lot of boron. All right, now the number of the hole density is pretty much the boron density. And vice versa for the electrons. But you end up with a balance of the other type, thanks to those thermal carriers that are bubbling around. You know, some random thermal carriers that show up and annihilate, but then there's some left over. And we can calculate what those must be. So let's see. Yeah, so let's restate this real quick. All right, it's kind of a summary of terms. If you add boron, that's going to add holes. It's the boron density is the number of acceptors, n sub a. It produces p-type silicon. Its majority carrier is a hole, and its minority carrier is an electron. So you mostly fill the thing with holes, but that means there is a balance of electrons in there. Conversely, arsenic or phosphorus, you're adding in a lot of electrons. That's the number of donors. You're producing n-type. Silicon, its majority carrier is an electron, and its minority carrier is a hole. So I've got these two types. So these majority and minority carrier concentrations, big caveat here, at thermal equilibrium, and applying a voltage takes it out of thermal equilibrium. So a semiconductor just sitting on the shelf, doped in whatever crazy pattern you want. At thermal equilibrium, we can use the mass action law, which is not a phrase the book ever uses, but this is what it's called. It's called the mass action law. And it tells us that the product of N times P, the density of electrons and the density of holes, right? Again, the electrons and holes that result aren't necessarily equal to the number of atoms we add, but for the majority case, that should be approximately equal. The product is always equal to Ni squared, the number we calculated earlier. Now, if you've encountered something like this, or you start to think about accounting for all of the charges, you might think it should be the sum, not the product, right? If we have this source of bubbling away thermal carriers that are generated, and I'm introducing a lot of one kind, they should annihilate one-to-one all of those and leave the difference left over, not the division, but the difference. And all I can tell you without going into too much spiraling rabbit hole detail is it's a product in large part because these are statistical quantities. They are not values. These are probabilities of becoming electrons or holes. And probabilities you have to multiply in order to combine them. You can't just add and subtract. So the mass action law tells us that it's the product, and we're going to depend on this over and over again in order to figure out what's going on in the material. So for an N-type piece of silicon, we're going to say, or we know, just by the fact that it's N-type, we know that there's a lot more donors. We know that ND is much, much larger than NA. And we can say N, the actual carrier density, is pretty much the same as the number of donors. I'm just going to say that that's pretty much equal. So that leaves trying to figure out the density of minority carriers, and we just use this expression. So we already know what N is, so we're saying P is Ni squared over N. That gives us what remains. And for P-type, it's everything backward. I'll write that out real quick. For P-type silicon, we know that the number of donors must be much, much less than the number of acceptors. The density of holes is approximately equal to the number of acceptors, and the density of the minority carrier electrons is equal to Ni squared over P. And since N is about equal to ND, then you could substitute ND in here. Na could be substituted in here. You see various forms of those equations sort of traded around. Once you start with these approximate equalities here, you can substitute kind of depending on what piece of information you know. Again, the full Harrier equations are in the book. That's equation, I think it's 2.6.1. Make sure of that real quick. You might have, this is 13, not too far. No, oh, is it actually section 2.6.1? There we go. Yeah, there we go. This nasty thing, blow that up. right? If you've got some donors and some acceptors, you can turn the crank on this thing, but you never end up needing this, because if there are some donors when you're having majority acceptors, it's 6 orders of magnitude bigger, and so this is just a teeny rounding error. Section. There we go. Fix my notes. All right. So that's accounting, and we're going to kind of switch gears to mobility next. So is at least the jargon and terminology all kind of grokking. We'll care more about minority carriers later, because it turns out if we exhaust all of this, we find a way to get rid of all of them, that can impact the behavior of more advanced devices. But for now, we're just trying to get a handle on what is in the semiconductor, how are we changing silicon, and how do we describe those changes? We have kind of magically added a bunch of other material, other atoms into the silicon lattice. What happens? What does it look like? We're just looking at a piece of shiny metal. Well, what's actually bubbling around under the hood? And this is how we describe it. We're talking about densities of all sorts of things. We just want to make sure we get it all straight. Yeah, go ahead.
Is like the scope of the size we're looking at like a single transistor, a full chip, or?
Yeah, so this is every kind of unit angstrom almost of every chip or transistor throughout, I'd say, let's see. So a diode is basically a sandwich of a p-type and an n-type material. You just take those two, squish them together. We care about the maybe couple of microns at the interface between the p-type and the n-type, and the rest of it is just homogeneous, unaffected. It's basically a low resistance thing that we've doped, right? The resistivity has changed because we added a bunch of stuff, but it doesn't have any kind of special properties. So at the resolution, I guess, is at interfaces between different types of doped semiconductor materials, rather than large swaths of it. You could use some of these doped semiconductor materials as wires, and we certainly do. But we don't care a whole lot about a lot of these details. We really only care about what we talked about last class, which is resistivity and conductivity.
So the scope of some of these equations are more for like maybe like a single diode and add its interface, rather than like maybe like the, I don't know, an I9 and like the single, what is that, 2 nanometer transistor, whatever.
Well, a single transistor, yes, that then gets built up in an entire network. I guess, right, the answer is all of them, because at the smallest scales, these numbers impact performance of individual transistors, diodes, and other semiconductor solid-state devices of many, many different kinds. But it's those performance parameters that turn into things like battery life of a phone. So it stacks on top of each other. If you could magically change some of these fundamental numbers, you would radically change how technology behaves today. Especially for the example earlier about the maximum temperature that any of these things can withstand.
Okay.
Maybe that perfectly doesn't answer your question, but.
Doesn't, but it's close enough.
Okay, great, good. Anything else before we switch and talk about mobility? So now it's just sort of more vocabulary introduction almost. All right, great. We talked about mobility briefly earlier. Anybody remember that bit? What does it, you remember kind of maybe there's an intuitive explanation. I think I talked about viscosity a little bit. Yeah, go ahead.
Electrons typically move faster than holes do.
Electrons move faster than holes, right? A lot of that is just physics, right? If you have a ball and you want to move it, that's great. If you have a whole line of balls and one's missing, and you've got to move one ball and another ball and another ball and another ball, that's just going to take time. And at the smallest atomic scale, subatomic scale, that's true too. So mobility just describes the response of a particle that's free to move, right? So, one of these majority or minority carriers, its response in the presence of an electric field. You apply a voltage, and what happens? How fast can it move? And that speed then impacts how fast it can react. It impacts how much current flows in response to voltage. And it's going to form kind of a core, almost assumed constant later on of a bunch of the MOSFET other transistor equations that we're going to develop later. But we've got to figure out what mobility is first. Let's see. Mobility. I just sort of say, how tough is it to move an electron or hole through the material? I guess it's not leaping out of the material, so how tough is it to move this thing in the first place? In the presence of an electric field. It's abbreviated as mu sub n and mu sub p, the mobility of the n-type things and the mobility of the p-type things. For whatever reason, even though we talked about electrons and holes, now we switch to negative and positive. I don't know why, that's just how the industry developed over the course of 100 years or so. And so we're rapidly getting away from donors and acceptors and electrons and holes into N and P. And N and P is going to be attached to everything after that. We N-type MOSFETs, P-type MOSFETs, NPN transistors, PNP transistors. It's negative and positive, but we've just got, you almost need this lookup table of, okay, what is N correspond to these things and corresponds to this device, and this corresponds to this kind of atom. We have not been consistent over the many decades of this industry, and I apologize. So it's mu sub n and mu sub p. The units are centimeters squared per volt second, which is just kind of a hack so that when we apply an electric field, of strength E, that's in units of volts per centimeter. A lot of centimeters in semiconductors, no meters. Should probably be microns these days, but it's centimeters, that's standard. So the unit, so volts applied over a given distance, volts per centimeter. So you end up with the product of these, centimeters squared per volt second times volts per centimeter equals centimeters per second. You end up with a velocity. So it just describes how fast the thing moves in response to an electric field of blah strength. You crank up the electric field strength, and the thing should move faster. Forever and ever and ever until you hit max speed is about 10 to the 7 centimeters per second in silicon. Pretty quick. This is the third of many times we'll encounter the word saturation in this class. This is velocity saturation, when everything's hitting the maximum speed. All right, we talked about there's a saturation state in BJTs. There will be a saturation state region of operation for MOSFETs. There's velocity saturation. There's a lot of saturations flying around. None of them are the same thing. They all use the same word. It can be pretty bewildering. So here's a funny thing. When you add dopants, you add more boron or you add more arsenic or phosphorus, the mobility goes down, which maybe kind of makes intuitive sense. There's just more stuff in the silicon lattice, and it's actually harder to move the electric field, harder to move things in response to electric field. But you are adding so many extra carriers, you're adding so many holes or so many electrons that the current still goes up. The effective current still goes up. you take a small hit in mobility, but a huge boon in just quantity of carriers that are able to flow in response to this electric field. And so you still end up with a material that goes down in resistance. It ends up being able to conduct more stuff. There's just more stuff around. It's moving a little more slowly, but there's just a lot more of it around. It's a weird kind of counterintuitive thing. The plot that I had queued up earlier right here, this is the kind of full nasty mobility expression for electrons and holes in silicon. You can see if you start adding more and more and more atoms, and the scale goes from 10 to the 13, barely any. That's only a couple orders of magnitude above the kind of thermal background of 10 to the 10, up to almost the most that you can pack in before it stops being silicon and starts being whatever material you're adding. Right? Past here, past 5 times 10 to the 22, you've hit the density of atoms in silicon. Everything between there, you see the mobility starts at about a third for holes. It holds about a third of electrons, and then it gets worse and worse and worse and hits this sort of minimum plateau down here when you get really high densities. But at these high densities, this is only going down by, a factor of 5, factor of 4, right? This one's going down by factor 14 maybe. But the number of carriers has gone up by 8 orders of magnitude. Just an incredible increase in available carriers to move for a pretty minor hit in mobility. These are the quote-unquote exact equations. They're only exact because they fit this curve. This is entirely material science curve fitting stuff, right? What we as a community did was doped in many, many fine gradations. We measured mobility at every point and then developed a function to curve fit it. So mobility tends to be something you know ahead of time, you assume. You could calculate it if you wanted to do a bunch of painful math. The thing to the 0.68, right? That's crazy. There aren't really physical laws we're trying to model here. This is just sort of what happens, what ends up happening in a lattice. So let's go back to resistivity. Now that we're doping, we're talking about how well any of these materials can support motion in electric fields, a return to resistivity. So at the introduction to this stuff, I asserted that the resistivity of undoped silicon was about 10 to the 3 ohm centimeter. For intrinsic silicon, that's blank, neutral silicon, just pure silicon. Call it intrinsic then. But now we have all of the stuff necessary to calculate what that really should be given the mobilities that and the charge densities that we might impart. 1 over the resistivity, conductivity, and that turns out to be equal to the electronic charge, right? 1.6 times 10 to the minus 19 coulombs times n. That's the density, so that's probably the same as n sub d in a majority n-type material times the mobility of those n-type devices, n-type particles, plus p times the mobility sub p, close parentheses. So again, these are carrier density and mobility. So now for any arbitrary piece of silicon that you have added or not added a certain amount of boron or arsenic and phosphorus, you know what N should be, you can calculate what P should be if it's N-type or vice versa using the mass action law. You can use that plot that I just showed to estimate what the mobility should be, and you can figure out what the resistivity must be for a given material. If you take the conductivity and apply an electric field, multiply it by E, you end up with what I wrote above times the electric field. Let's do that real quick just to make things clear. Q times N mu sub N plus P mu sub P times the electric field. Now if we distribute all this stuff around and intentionally draw the polarities to make things clear, we can say that can be expanded to Q times N, negative Q times N, times negative mu N times the electric field plus the opposite, Q sub Q and P, and positive mu sub P times the electric field. Now we've got things grouped in charge density, that's in units of coulombs per cubic centimeter, and velocity, like we showed earlier, centimeters per second. Charge density times the velocity ends up being something like current. It's current density instead of just current. That equals what we abbreviate as J, which is not the square root of -1 in this case. This is current density, amps per square centimeter, the number of amps per unit surface area flowing through a two-dimensional surface. We've got something that kind of looks like Ohm's law, right? We've got a current density, we've got an electric field, and we've got conductivity. It's close, but not quite. Multiplied by all the actual dimensions in order to get real voltages and currents and resistances. It's sort of a per unit size, per unit area, per unit volume equivalent. So if I illustrate all this stuff, I drew this box earlier. Now we can add some more stuff to it. Now we've got a box with cross-sectional area A. We've got a current flowing through it, I, in response to a voltage being applied, V. We've got a material with resistivity rho, and we've got a length L. So we've got material properties, we've got electric field that's being applied, we've got dimensions, and we've got current that's showing up as a result. We start with Ohm's law. Well, we can substitute the resistivity equation that we talked about last time. So that's actually I times rho length over area. We can rearrange some variables. We end up with voltage over length equals current over area times rho. This is the electric field. This is the current density. And this is 1 over the conductivity. Move things around, that's equals to, we'll just on arrow, E equals J over rho, or E, sigma rather, equals J. So we're back to the expression we just wrote on the last slide, just moving Ohm's law around in order to be in units of, or with respect to, all the stuff that we know how to calculate about semiconductor states instead of things that we're applying and overall resistances and overall currents. We can take all the stuff that we're looking at the lowest levels, figure out how many charge carriers exist, figure out where the mobility is, and build up how the device should behave in a circuit from there in response to what we know about Ohm's law. I'm going to bring it all full circle. This is called drift current. I have no idea why. The etymology of this term still escapes me.
Because the electrons are drifting.
Right, but why are they? Drift feels to me like they're just sort of floating along with no external force, as opposed to applying a voltage. Yeah, seems weird, seems a little counterintuitive to me, but when you apply a voltage to a thing and current flows, that current is called drift current. And I need to specify that because we're about to introduce a different kind of current called diffusion current. That is not because of an applied voltage. It's because of crowding. If you have a pile of electrons in one corner and no electrons in the other, and somehow you're able to keep them still for a little while, and then you let go, and they all flow in one direction, that's like a current. That's diffusion current. Any diffusion works like that. A little blob of ink in the corner of a cup of water, there's going to be ink flow because of the diffusion. You're going to be like the ink is flowing from one end to the other. It's really diffusing to be kind of equally distributed everywhere. But while it's on the move, that's a flow. Same thing with currents. If we have too many electrons in one area and almost none in another area, the electrons are going to flow from one side to the other. And in that brief moment of time, it's going to look like there's a current that's diffusing from one to the other. Same thing with holes. They have a big pile of holes in one corner of the semiconductor and none in the other because of some steady state issue, or you've just taken a p-type and n-type material and stuck them together, and there's a lot of holes on one side, a lot of electrons on the other, and you need to flow across that barrier in order to diffuse and make it so there's kind of an equal number everywhere. That moment is diffusion current. And the easiest way to illustrate diffusion in any plot is or in 2D, I suppose, is to say, we've got on the y-axis, we've got density, and on the x-axis, we've got, well, distance. And we usually just draw a straight line, something like that. We just say, measuring over some distance, we got some material, maybe a picture. It's about the same. Let's make these about the same size. Let's say we have a block of material, and the density of carriers over here is pretty high, and then there aren't a whole lot, and then there's really very few at the other end. Pretend that that's a gradient. That's a linear gradient. So on one end, at this end, we've got a really high density of stuff, and the other end, we've got a really low density of stuff. And this stuff could be anything. Again, ink In clear water, could be some gas release that is slowly diffusing through a room. Anytime you're trying to do ventilation, you're worried about, or trying to leverage diffusion gradients. And of course, in the context of this class, if you have a big pile of electrons for whatever reason on one end and not many at the other end. You could have a step function. You could say there's a whole lot here and 0 in the rest of it. But having a line makes the math a little bit easier because there's a partial differential equation that you have to at least think about. If it's a line, that makes the math really simple. So we draw this straight line. If there's so we'll just say qualitatively, there's lots. Oops. There we go. Lots over here. Oops, that shouldn't be the axis label. Lots and few at that distance. Then this is not at steady state, right? Nothing is in equilibrium here. You kind of somehow are enforcing this distribution, and then you let go. You would describe it as flowing that way. Some of the things are going to just sort of flow in the other direction, and eventually it's going to flatten out. Everything's going to be equal. If the thing we're talking about is the stuff in p-type carriers, if it's holes, if it's p-type majority carriers, the flow direction is also the same as the current direction, because we have, for whatever reason, defined the flow of positive charges, which don't exist, as the positive direction. Say if let's see. So for this flow direction, if it's holes, current flows that way. But if we're talking about electrons, the current is actually pointed the other direction. Right, the electrons are all going to fly this way. That's the density. That's the gradient. But since their electrons are negatively charged, it's going to look like a current is flowing in the opposite direction. One more way to get signs backwards. Current flows in the opposite direction. And you can imagine this could get more complicated. Right? This linear function can be all sorts of shapes and sizes. But just to illustrate something like this is an easier kind of toy problem. Yeah, let's make a new slide and say the diffusion current equations J and diffusion. Now we've got all sorts of tags. So we've got current density J of n-type devices, n-type carriers, electrons, and we've got it tagged with diffusion current instead of drift current. That is negative times the electronic charge times this magical diffusion constant called the diffusivity times the negative partial derivative of the density of those devices along X. This is where it being a straight line would make the math, it will make the math a little easier. And conversely, diffusion of p-type, d sub p, the p-type diffusivity times partial p P partial X. This thing the diffusivity in centimeters squared per second. I think this is sometimes called the Einstein diffusion equation, even though I think 3 people independently discovered it at the same time. That constant is either substitute the end of the P as you need, because on the other side is mobility of N or P, depending on which one you're talking about, times Boltzmann's constant again, temperature, and the electronic charge. So it's the mobility times this thing that we're going to be talking about a lot. This we abbreviate as V capital T. This is the thermal voltage. Kind of describes how much voltage it takes to get anything done per unit charge at a given temperature, kind of. It's going to show up in lots of places. At room temperature, at 300 K, this is about 26 millivolts. That's a great number to just tattoo on the inside of your eyeballs right now. V capital T, 26 millivolts at 300 K. Unless you know the temperature has changed, you're talking about cryogenic systems or superheated jet turbine situations, 26 millivolts. You just sort of plug that in and forget about it. I think it's actually 25.6 or something like that. But we just always just kind of say it's 26. VT ends up showing up in device equations, in diffusion equations, in all sorts of stuff over and over and over again. And just sort of knowing ahead of time, oh, KT over Q, I've seen that before, 26. There, you just saved yourself 5 minutes. Add that up over an entire career, you could save maybe a whole day. This is not V sub little t, the threshold voltage. Get ready to mix these up a lot. The threshold voltage is what we describe in MOSFETs as sort of that magic point at which the transistor can be considered on. It usually takes maybe 200, 300 millivolts, something like that, before there's enough of that conductive bridge between the source and drain to do anything. Until that happens, until you get what we call inversion, until you get enough carrier sort of pulled out of the depths, out of the silicon lattice, nothing happens. So below the threshold voltage, you basically, the transistor isn't doing anything. And once you get past this sort of magic number, it suddenly pops into a different region of operation. And in small devices, in transistors that are really, really narrow width, the concept of threshold is a little softer. The device starts to sort of warm up and is starting to provide some gain. And then you pass the threshold voltage and then it's sort of solidly in saturation, it's solidly on. And so the threshold isn't really a threshold, but more of kind of a soft knee in the response curve. We go from having things that look like this to things that look more kind of like this. You're like, well, where's the threshold points? Is it in here, I guess? But anyway, threshold, V sub little t, will show up a lot later on as well. Very different than the thermal voltage, but unless you're paying attention to subscripts and context, they'll be all over the place. Beware. Okay, so let's do the math, combine these things, and end up with a total current density expression. So J total, which I'll abbreviate as just a capital T in a second, that is the sum of the drift current. Again, the drift current is just what happens when you apply voltage. So if there's no voltage applied, that's 0. Plus the diffusion current that happens just from there being too many things on one end and not enough on the other. So when I said that if you're not applying a voltage, drift current is 0, that is true unless you end up with a voltage that gets applied intrinsically inside the device. And that is one of the hardest things to kind of imagine in diodes when we start talking about when we have a p-type and n-type device next to each other. First, you get diffusion. First, there are lots and lots of holes on one side and none on the other because you've got a p-type material over here. And then there are lots and lots of electrons over here and none on the other because you've got n-type material over there. So the first thing that happens when you bring these two p and n types together is this rush of electrons from one side into the p-type material and electrons, holes from the p side into the n-type material. So there's this huge initial diffusion current. Now, when each and every one of those carriers diffuses somewhere else, they leave behind a proton that is stuck in place, or they leave behind a filled hole, and so there's an electron that's stuck in place. So as this diffusion flows, they leave behind oppositely charged regions of doped semiconductor. Just like we talked about it, I won't flip through 10 slides over and over to illustrate it. But remember how when, so for an n-type material, you've got 5 electrons. One of them is free to move around. It takes off. There's still that fifth, or that extra proton left in the nucleus. And so that local region is now a little bit positively charged. So imagine that happening en masse in a p-type as all of its holes drain out into a region that have no holes. And in an n-type where all of its electrons drain out into an area that has no electrons. That's what happens when you bring an n-type and a p-type device together. What that ends up doing is creating a voltage inside. So you've got all these fixed in place negatively charged atoms, all these fixed in place positively charged atoms. They're just stuck. They're not free to move. There's a static electric field that forms between them. And so you end up with drift current suddenly. So you start with this rush of diffusion current from the p-types and the n-types into the opposite ends. Then you end up with this drift current that shows up because now there's an oppositely pointed electric field that appears because of what's left behind after all this diffusion. And eventually they match, they equal each other. And for the diodes that I passed out on the first day of class, right, current is not flowing through those, which means diffusion and drift have balanced, and they're equal and opposite, and the J total must equal 0. And for a higher density of doping on one side or another, the amount of region that you need to flow away, the number of devices that have to diffuse out in order to reach that equilibrium, that will change. That changes the physical size of the area that is totally depleted of carriers. So you end up with, you have a really high density of dopants on one side and a low density of dopants on the other. The low density side has to give up just more physical space. And so this region that has stood up this electric field, this region is just larger on the lightly doped side because you need more volume of the doped semiconductor in order to compensate for the same number of devices on the other, same number of atoms on the other side. We'll illustrate a lot of this stuff later on, but developing the intuition is maybe the hardest part of this class. of what happens when you bring a P and N type device together. What kind of, you think of it happening live as you bring the two together, where do the charges flow? Where are the fixed charges? Where are the mobile charges? How does it end up resting at steady state? You figure that out, then we're gonna mess with it by applying external fields and flowing current through. Other things happen. But if you can kind of figure out how the system starts, then you'll be in a good place to figure out how the system changes when we add external interference, basically. All right, so that's drift and diffusion, and I'll add actual expressions now. So J total for N-type. If you take the expressions we've written before, do some substitution. I'm skipping a couple steps here. Right, we've already got to go back one. Right, we've got stuff like this diffusivity constant we can substitute into these equations. We wrote current density equations for drift current earlier. Just take it on faith that I've pulled those out and rearranged some expressions. You can go through the algebra yourself, of course, but to kind of cut to what I think is the most useful form, the N-type is Q times u sub n times n, the density again, times the electric field plus, there's the thermal voltage again, 1 over carrier density, partial n, partial x. And you do a lot of probably unsurprising substitutions. N for P in the P-type, the electronic charge times mobility, P times the density, electric field now minus VT, 1 over P, partial x. This is equation 2.17. In the book, they go through the more detailed steps of substituting and moving the variables around and everything. But this is, I think, probably on the second homework, we will want to use these equations to show that for a p-n junction, there must be that electric field that I talked about earlier. There has to be an electric field that holds back the continued diffusion tide. There has to be something that is providing an equal and opposite drift value. Because for something that's at rest, something that where the total current flow is 0, these have to equal 0. And so if these are equal to 0, what you should be able to show is that the electric field must be non-zero. And you can even go so far as to assume some dopant quantities, figure out the mobility, and solve for what that electric field must be in order for all these things to add up in equilibrium. So far, so good? All right, that's as much of chapter 2 as I wanted to throw at you. There's plenty more detail in there about semiconductor devices and device physics and stuff, but I feel like this is the core of what we need to underpin understanding the rest of the device. I would recommend taking a look at chapter 211 for fun. It's like 2 or 3 pages, and it's about how semiconductors are actually fabricated, how chips are designed. Right? We started with this idea of taking a block of silicon and putting it in a superheated gas environment full of boron. Okay, so that's how you make a p-type device, but how do you end up building a transistor out of this? And it's many, many steps of carefully drawing masks so that some parts of the semiconductor experience that superheated environment and the boron's able to soak in, and some parts are blocked from that. And you peel off the mask, you draw a different mask, and you soak in N-type, and you peel off the mask, you put another mask on, and then you sputter. Sputtering is exactly what it sounds like. It's just taking metal and going at the thing. You rain metal down, And then you peel up that mask, and it tears up all the metal that wasn't that was on the mask. So the mask rips up the metal, leaving just the negative of the traces. And you do that over and over and over and over again, a couple hundred times, not that many, but many, many times, and eventually build up what you think of as a chip that you can see these cross sections and illustrations of. But they've got some nice pictures of kind of how that looks step by step. And if you haven't seen those kind of side profiles, what it looks like, if you take a chip and kind of saw it in half and see the layers built up, this is going to be a key to read through in the book, and then you'll be able to sort of Google stuff like this and understand what's going on later on. You'll see these sorts of illustrations over and over again for the rest of your career. So you get a little bit of exposure to it now, you'll sort of go, oh yeah, okay, I kind of recognize how this works. It takes a little bit of brain bending to kind of imagine how this 3D object has been sliced and is being represented in 2D space. But if you can wrap your head around that, I think it's interesting. I personally think it's really interesting. It's relevant to kind of how this stuff is really made. It's not part of the anything that we're going to put on the exam or homeworks or anything like that. It's just kind of a nice thing to understand about the chip design and fabrication industry. All right, any questions about all this stuff before I, yeah, go ahead.
So the VT capital, is it the thermal voltage?
That's thermal voltage, that's right, yeah. We'll get into threshold eventually, but for now, all the VTs are going to be thermal for the next couple of weeks, probably. Yeah, but good instinct. All right, be skeptical of every VT and go, hang on, is this thermal or is this threshold? Yeah, good question.
Just write VTH for threshold.
All right, so remember there's that very brief quiz online. Please submit that in the next 24 hours or so. Homework 1 is posted, and yeah, operators, especially on the discussion board, are standing by. Yeah, keep in touch. I see right outside our TA's shown up, so just like we talked about in the syllabus, I'm going to swap out. He's going to be available for the next hour or so for office hours, unless there are no questions, in which case he'll